Hi everyone, welcome to this presentation. My name is Atindriyo Kusumo Pamososuryo. I'm from Delft University of Technology, and today I would like to present my latest work with my colleagues Yichao, Riccardo Ferrari, Tobias Gybel of Hovgaard, and Jan-Willem van Wingerden on blade effective wind speed estimation, a subspace predictive repetitive estimator approach. As a start, let's take a look at the wind power growth over the past year. Despite COVID-19, 93 gigawatts of new wind capacity have been installed, and which makes the total global wind power capacity to 743 gigawatts. However, this is not fast enough, and the global wind power still needs to grow 3 times faster over the next 10 years to keep the global warming below 2 degrees Celsius, or at least 180 gigawatts of new wind capacity needs to be installed every year. In order to achieve that, we need our wind turbines to be larger. These days, for example, we have on average 2.5 megawatts of wind power for onshore sites and 6 megawatts of wind power for offshore sites. As we can see here, the rotor diameter for the onshore is about 120 meters and the hop height is about 90 meters, while for the offshore, the rotor diameter is about 150 meters and the hop height is about 103 meters. But in the future, we'd like to capture more energy, more power. So the rotor diameter needs to be increased. For onshore, it needs to be increased until 174 meters approximately, and hop height is about 130 meters to capture 5.5 megawatts. And for offshore, to capture 17 megawatts, we need to increase our rotor diameter to 250 meters and the hop height to 151 meters. However, larger turbines give more challenges to control design. For example, anemometer and wind vane measurements will be less valid since the wind speed varies more over the rotor area, and such inaccuracy will deteriorate the controller performance and can be detrimental to the wind turbine. Therefore, we need a more representative information on the wind speeds, that is the blade effective wind speed. Unfortunately, there is a knowledge gap here because this information is not always available such that someone has to think of a way to estimate the blade effective wind speed. As we will show later, such information can be derived from the blade load measurements. In our work here, we propose a solution to use a fully data-driven blade effective wind speed estimator. In this scheme, we have our wind turbine, which is NREL 5 megawatts, and we have the SPRE, which is the Subspace Predictive Repetitive Estimator, and we also have azimuth-dependent cone coefficient here. Here, the turbine outputs the measured blade root bending moments, which is denoted by the M123 here, and these are subtracted by the estimated blade effective blade loads measurement from the azimuth-dependent cone coefficient, which result in the errors for the first and second and the third measurements here. And these are taken by the SPRE to generate the individual estimated blade effective wind speed. And these are also fed back into the azimuth-dependent cone coefficient to estimate the blade loads. Here, the SPRE consists of two subsystems. The first one is the subspace identification, and second one is the repetitive estimator. And the former is used to formulate a linear approximation of the wind turbine dynamics, while the second one here, the repetitive estimator, is used to estimate the periodic wind inflow over the individual blades. Here we see an example of an azimuth-dependent cone coefficient for one azimuth position. As we can see here, at the vertical axis, we have the CM1, which is the cone coefficient for first blade, and we have here the tip speed ratio. We also have the blade pitch angle, and we have the following contour representing the cone coefficient itself. And here we have the cone coefficient equals to the blade root bending moment divided by 1/2 of air density times rotor area times rotor radius, times the reference wind speed squared. And of course, this is also done for other azimuth positions to capture the variations over different blade positions. Now let's continue to take a look into the repetitive estimation step. The measured blade loads here are firstly stacked into a lifted domain, and then the receding horizon optimization based on the linear model coming from the subspace identification step is used to estimate the blade effective wind speed. And in this algorithm, we use basis function to project the measured blade loads and hence approximate the linear model into a lower dimension. And this will significantly reduce the computational complexity. Now let's take a look into the simulation results. In the first case here, we have a stepwise shear wind condition. In the first figure here, we have the estimates of the wind speeds, and we have the in this axis the azimuth positions. So as we can see here, because we are using a sheared wind, we have the wind goes lower into lower wind speeds at about 180 degrees because that's where the wind speed is at its lowest according to the wind shear model. And here in the second figure, we see the wind speed evolution, and we can see here the reference value, which is the stepwise wind here, and we have also the mean wind speed from the SPRE, which is shown as the blue lines here, and also the blade effective wind speed estimation shown in this black line in a sinusoid kind of behavior. And here we see at about 10 meter per second our wind speed estimate, and we can also see at higher wind speeds, for example at 12 meter per second, and we can see that the figure above here, the wind speed goes higher, and we see also at 14 meter per second, and the wind speed also it goes higher as well. And of course, due to the use of the wind shear, we have a wind deficit at about 180 degrees. Now we can see that this method is actually effective in monitoring the periodic wind inflow on a blade. Now in the second case, we consider a more complicated wind condition where our wind turbine is overlapped by a wake shed from an upstream turbine in a wind farm setting. So as we can see here in the first figure, we have the dimension of our area of inspections. We have the height and the width in meters, and we see here that the wake is being overlapped over our turbine. And here the black circle shows the rotor area of our wind turbine. And at the right hand side, we have the wind speed estimation here. You can see that it detects the wake overlapping because we see some wind speed deficit here, and that is because that wake overlap is captured by the blade root out of plane bending moments, as we can see here in the second figure. And the last figure here is actually the evolution of our coefficients of our basis function over time. So this simulation shows that actually our proposed method can also detect a wake impingement over a rotor area, which can also be useful, for example, for wind farm control purposes. Now let's take a look a little bit deeper for the last case again. And this figure shows the snapshot of the wake overlapping case about 540 seconds and 740 seconds. And we can see here, this is the wind speed, and x-axis is the azimuth. As we can see here, the first figure from 0 to about 200, we see that there is a wind deficit. And at the second figure, we have wind deficit at about 200 to 360 degrees. And this means that the SPRE can also be used to detect a propagation direction of the wake of a wake impingement. So we're now at the conclusion of this work, and we have shown that the SPRE is effective at estimating the blade effective wind speed in the stepwise sheared uniform wind condition, and also it presents a successful estimation in a more complicated scenario where the wind turbine rotor is impinged and overlapped by a wake shed from an upstream turbine. And by identifying the velocity deficit, it is capable of detecting the wake interference and identifying its propagation direction. In the future, we would like to assess the effectiveness of our estimator in a more realistic wind cases, such as turbulent cases, and also improving the accuracy and reducing the delay. And finally, we would like to see if our estimator can be used together with advanced control methods such as model predictive control and see how it can improve its performance. Thank you for your attention. If you need more information, please contact my colleague Yichao Liu. And for now, I'd be happy to answer your questions.